Okay, so let's have a closer look at similarity, dissimilarity, and stuff like that. So dissimilarity, I told you that is typically what people use. Yeah, so not similarity measures. Very often they just use dissimilarity or distance measures, and that follows typically the idea of a geometric approach. So the objects are defined by their kind of perceptual representations in some perceptual space, and the perceptual space should somehow represent the psychological space. Yeah, that's what you have in your head, so to say. Yeah, because you derive those features from the raw objects that in your head are the most important ones. Yeah, or the most important to the head of some expert. Yeah, and then you follow, and that is the geometric approach. Then you follow this geometric distance. So you compute the geometric distance between these perceptual representations, and that defines in that case, dissimilarity of objects, and in turn the similarity of object, of course. Yeah. So within the scope of our feature-based similarity, it means that the perceptual space is the feature space. Yeah, the mapped feature space. So this one here is the perceptual space. That's what I just said. We try to extract important features which are important to our idea of what is actually in the data. Yeah, what is the similarity about? Yeah, so we try to model those features that in our mind are important for deciding about the similarity of the raw objects. Yeah, and that is the perceptual space, which is the feature space or the feature representation r to the power of n, which is f. Yeah. And the geometric distance is just a distance function in this perceptual space. So, for example, it could be Euclidean distance or stuff like that. Yeah, we'll talk about that in a couple of minutes. So, distance functions. So the distance measure is a distance function if it is also reflexive, non-negative, and symmetric. You just recall that from your math courses or your math lectures. So a function in a mathematical sense is reflexive, non-negative, and symmetric. Not all distance measures need to be like that. Yeah, so in that case you should call it a distance measure. If it is really reflexive, non-negative, and symmetric, then it's also a distance function. Yeah, it's just a kind of syntactical sugar, so to say. No, it's not, because different things have different characteristics. So a distance measure have some different properties than distance functions. Yeah, and very often people, I think I told you last week already, make a lot of ado to talk about distance matrices. Yeah, so a distance function is a metric if it's reflexive, non-negative, and symmetric. Otherwise, it wouldn't be a function, of course. But it is also a metric if it additionally satisfies the triangle inequality, which you probably know. Yeah, and the nice thing about matrices is that they have a sound mathematical interpretation, allow domain experts to model the notion of dissimilarity. Nice. Metric distances typically allow to tune efficiency of algorithms, actually. Yeah, so that is that is the real reason why people pretty often care about matrices, metric spaces, or metric distance functions. Yeah? But once again, there is actually a long-lasting discussion whether or not these metric distances, especially the triangle inequality, is really what we as humans have in our intuition. Yeah? So here is a kind of contradicting example. So the distance between, so if the triangle inequality holds, the distance between these two images must be smaller or equal than the distance between those two plus the distance between those two. Yeah? And if you have a closer look to this, so this sum here must be larger or equal than this distance here. Yeah? And if you have a look at this one here, well, depending, of course, on the distance. But now let's just take our intuition, our human intuition, and we'll say, okay, those two here will have a very, very small distance, because both objects in the images are round, yeah, are somehow balls. The ball of the moon and a football, a soccer ball. Yeah? And also the distance between these two images are probably much smaller because they have both a black background and the luminosity is not very high and stuff like that. Yeah, so we have considerably small distances here summed up. So the sum is also considerably small, but those two images are actually completely different. Yeah, so they have completely different objects on it. They have completely different luminosity and stuff like that. So they don't share really many properties, probably no properties at all. Yeah? So the distance between those two intuitively, I'm just arguing intuitively, is probably quite high. So it's probably not the case that this distance between those two objects, between those two images, is smaller or at least equal, or at most equal, than the sum of those two distances here, of images which are pretty comparable. They are not similar, of course, so these distances won't be zero, but they are the sum should be much smaller than this distance, this sole distance here. Yeah. So there's a kind of contradicting example to this metric property, especially these inequality properties. So that just keep your head on or heads up to this discussion about whether or not you need a metric distance function or not. Some algorithms actually are designed to be a little bit more efficient, and they use triangle inequality properties in order to be a little bit more efficient. But still, those algorithms typically work if the distance functions that is used is not a metric. It does not satisfy the triangle inequality, because very often we have just as a distance function a pseudometric, which means that in most cases this distance function acts as a metric or behaves as a metric, but there are some rare exceptions where, for example, triangle inequality can be violated, and in that case it's absolutely okay to apply that. So don't be too afraid of using a distance function which is not a metric if it's appropriate for you. So the distance function should be, or the choice of the distance function, the most important consideration should be, is it really appropriate for this application? Does it really model the intuitive similarity for this feature space, for this feature representation I have, and not some kind of performance things. And this discussion, and that's the last point here, this discussion about metric spaces or metric distance functions is mostly about efficiency, not about accuracy, so to say. So revisited similarity versus dissimilarity. So we talked about it before. Now let's see if we can somehow transfer each other into the other one, so to say. So similarity, once again, measures similarity, so high values to things that are similar. Distances have low values to pairs of objects which are similar. And the question is, can we transform each other to each other? So we can do that with a monotonically decreasing function f, which defines then as, for using this decreasing monotonically decreasing function f, we can define a similarity function out of a distance function. So given a distance function in our feature space, we can design a similarity function by just applying this monotonically decreasing function. For example, we could apply the exponential function, we could apply the logarithmic function with 1 minus. We can use, of course, also a linear transformation with 1 minus the distance. And you see here different scales, and the point is basically the transformation is always a little tricky, because distances range from 0, perfect, or just take the perfect similarity. So just take the two times the same object. So the distance between the same object and to itself is 0, the similarity between the object and itself is the highest possible value, whatever that is. Yeah. So you see how to transform these different ranges of values that can come out of these different functions, yeah, or different measures. So this is typically the problem. And yeah, very often you get here in that case the highest similarity is then 1. Yeah, because then for example, in the linear case, the distance between x and itself, so if y would be x, then we have a distance of 0. From x to x, it's 0, of course. Then we have 1 minus 0, which would be 1 would be the highest similarity possible. Yeah, in these transformations. And the other way around is sometimes a little bit different. Yeah, just keep that in mind.